على قناة اليوتيوب نتاع الجمعية التونسية للشباب الفلكيين. دونك أولا نحب نرحب بالجميع، مرحبا الناس الكل في محاضرة جديدة، في حلقة جديدة من برنامج أستروتالك اللي هو برنامج ممول من الاتحاد الفلكي الدولي، واللي يعنى بتقديم محاضرات معناها على قناة اليوتيوب للجمعية التونسية للشباب الفلكيين. المحاضرات هذه تعنى بمواضيع علمية وأيضا مواضيع في علم الفلك، وأيضا الأنشطة التوعية بعلم الفلك في تونس وأيضا في العالم العربي الكل. دونك ضيفنا اليوم هو الأستاذ أمين الزريبي. أمين الزريبي هو طالب في جامعة إيوت لوراند في بودابست، وهو أيضا عضو مؤثر علمي في قسم علم الفلك بالجمعية التونسية الشبان والعلم، ورئيس سابق لنادي البي.ام الديناميكي أو ديناميك الفضاء، وهو أيضا عضو في مكتب التوعية الفلكية بتونس التابع للاتحاد الفلكي الدولي. أمين الزريبي هو طالب ناشط وأيضا فلكي هاوي منذ سنوات كما قلت في جمعية التونسية الشبان والعلم، اللي هي أعرق الجمعيات التي تعنى بعلم الفلك والعلوم خصوصا. إذن أيمن الزريبي باش يعطينا اليوم محاضرة حول تكنولوجيا الاستشعار عن بعد وصور الفضاء. تفضل أيمن وتستطيع مشاركة الشاشة. شكرا.
Okay, thank you, Meza. So the conference is going to be in English. So I'm going to share my screen now. Okay, so can you see my screen? Can someone confirm that?
Yes, we can see your screen, yes.
Okay, so let's start. So our conference for today is remote sensing and deep space imagery. So first of all, before talking about remote sensing and deep space imagery, first of all, we're going to talk about deep space imagery first. But there is some fundamental laws that we're going to set before start in our discussion for today. So first of all, let us set some fundamental laws that govern the orbital mechanics of celestial objects. So if we're talking about orbital mechanics, let's talk about the movement of Earth. The movement of Earth, as there is a misconception, wide misconception, is that the Earth is rotating. Can you see my mouse? Okay, so the Earth is rotating according to this axis. But actually, the Earth is tilted by 23.26 degrees. And so because it's tilted, the celestial equator is also tilted from the ecliptic plane, which is the plane where all the planets revolve around the sun. So actually, there are four movements of Earth. So around the sun, which is 1 solar year, around itself, which is 23 hours and 56 minutes and 4 seconds, and rotation of its axis. This axis rotates between 26,000 years, and the oscillation of the axis due to moon gravitation. But in our conference in deep space imagery, we only going to discuss the movement around the sun, and of course the movement around itself, because the other movements gonna take thousands of years, and it's basically it doesn't alter any calculation. So for example, we have the Earth here, and we have our satellite, which according to the picture is orbiting the Earth, and we have 2 points here. So this point is called perigee, and this point is called apogee. And these 2 points are the extreme points between the orbit of the satellite. So the perigee is the closest point to the center of Earth, and the apogee is the farthest point to the center of Earth. But apogee and perigee is referred to the moon, and actually it should be a moon here rather than a satellite. So if we want to talk about orbital mechanics, let's talk about the godfather of orbital mechanics. He is Kepler. So this leads us to Kepler's law. So the first Kepler's law is law of ellipses. Kepler says that any object, any celestial object, any two celestial objects, if one is very massive and the other one is less massive, for example, let's take the sun here, and this is a planet. It could be Earth, could be Mars, could be any planet. The planet is orbiting in ellipse, and you can see this ellipse that has the major axis and minor axis, and the sun is in one of the two focuses of the ellipse. The second law of Kepler that states if we're gonna take, for example, this distance, which a planet travels from a certain time, let's call it a time t, and this distance that travels in the same time t. Kepler says that the area of this area x is equal to area y, and all these laws are the fundamentals of orbital mechanics, like I said, and honestly, you can do nothing without these laws. And the last law is Kepler's third law, is harmonic law, which states that the major axis, which is r, the cube, is proportional to the period of the rotation of any celestial objects around a very massive body celestial objects, of course, squared. And we have the Kepler constant here. So after talking about Kepler's law, let's start in the deep space imagery. So after defining the fundamentals, we need the telescope, a deep space imaging telescope. But the question is, why do we need it? We need the space telescopes basically because some radiation cannot reach Earth because due to atmosphere and ozone layer and many other factors, some radiation from deep space cannot reach Earth. So we need to take our telescope out from the atmosphere for in outer space, not very far, not in high altitudes, but further enough to see the deep space. So an example of our deep space telescopes, one of the famous ones, is the Hubble Space Telescope. It's launched in 24th April 1990, and for like 30 years or so, it's the Hubble Space Telescopes is sending pictures of nebulas, galaxies, deep space galaxies, and in many others. And we can see that the Hubble Space Telescope is basically in a tube shape. We have the solar panels here, and these some pictures of taken by the Hubble Space Telescope. So NGC is a new calendar. And a bunch of nebulas and supernovas, and this is my favorite, the pillars of the universe. And basically, the mechanism of Hubble is the light when it's gathered in this hole, it travels through the primary mirror, which is here, the yellow one, and the primary mirror is not a flat mirror. Because the type of this telescope is Ritchie-Chrétien, so the primary mirror is not a flat mirror, and it somehow, I'm not gonna go into details, but it somehow reflects the light, it bends it a little bit, and reflects it to this green secondary mirror, which is reflected as well to the capture and the instrument that's gonna take the picture and then send to the database of NASA to really check the picture to have a clear picture. So another space telescope is James Webb Space Telescope, which launched in 25 December 2021, so recently. And the difference between Hubble Space Telescopes and James Webb Space Telescope is we can clearly see the spectrum of light, so from X-ray to visible light, the light that we see, and infrared. So Hubble Space Telescope is between the ultraviolet and infrared. So it has the capacity to have pictures in or to have the ultraviolet radiation capped by its instruments, and the visible light, and also a small spectrum of the infrared. But the James Webb Telescope only can capture the infrared radiation. So these are the difference between the basic difference between the two telescopes. And James Webb telescopes help us in capturing the infrared to know much more information about deep space, and therefore the Big Bang and the start of our universe. But the question remains where to put it, where to put the new James Webb telescope. As you can see here, we have two celestial objects, the Earth and Moon, and the white lines here are called the Lagrangian points. So I'm sorry, the white lines here are the distribution of the gravitational forces of the system Earth and Moon, and the points L1, L2, and L3, and L4 and L5, like you can see here, are called the Lagrangian points. Basically, the Lagrangian points are the points that where the forces of Earth, gravitational forces of Earth and Moon cancel out, basically. So if for example, I'm gonna put an object in L4, it's gonna stay there no matter what. It will not be attracted by the Earth or Moon or any. Of course, I'm talking about only this system. Without considering other objects revolving around the Earth and the Moon. So let's watch a short video so that can describe where we can put the James Webb Telescope. So
Sun-Earth L2 point is where Webb's orbit around the Sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal
So as you can see, the James Webb Telescope is, we put it in the L2 Lagrangian points, which is behind the Sun, I'm sorry, behind the Earth, and it covers it covers it shields the space telescope from the radiation coming from the Sun. And of course, in this way, we're gonna have two faces. So we're gonna have a face in the James Webb Telescope that is towards the Sun, which can reach 85 degrees Celsius, and the other face or other surface of the James Webb Telescope, which had the mirror and stuff like that, can reach minus 233 degrees Celsius. So the difference is enormous.
Influences of Earth in all eclipses. Additionally, the Sun, Earth, and Moon, the brightest objects in the sky, are hidden by the deployed sun shield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery.
So as you can see, when we put the James Webb Telescope in the L2 Lagrangian points, it will not change the system that we had earlier, the Earth and the Moon, and we have for example, the Sun and Earth, and the James Webb Telescope will follow the point, and it will not change direction no matter what. So to find this, we need some basic mathematical and physical laws. So of course, we all know the Newton's law, which states the sum of forces equals mass times acceleration. So let me laser point. Okay, so we all know that the sum of forces is equal mass times acceleration, but because it's orbiting, we use a different form. So we have the gravitational Newton's law, and from both cases, from the Earth and the Sun, neglecting all the planets, and finally, after very short calculation, we're gonna end up with the three equations that governs the that shows the location of the Lagrangian points. So we have x as variable here, y as variable, and z as 0. So we have an equation of a plane where we can simulate this equation and the three equations actually, and we're gonna have, like you see, the 5 Lagrangian points. This is a 3D depiction of the gravitational distribution of the two systems, and these are the Lagrangian points where we can put the James Webb, and the James Webb we can put it only in the L2 Lagrangian point. So after talking a little bit about the deep space imagery, let's explore our Earth, but how to do that? Which are the principal things that we can explore, or tools that we can explore with our Earth? So basically, in this, we're gonna talk about remote sensing. What's remote sensing? What's the application of remote sensing? So remote sensing is everything that you have information about an object, for example, without touching it, without seeing it, without smelling it, and without tasting it. So if you have information about any objects around you in your environment, and you don't use your 5 senses to conduct those basically those information from, that's remote sensing. So the application of remote sensing is satellites, analysis, and graphs of even the imagery of Earth, like Google Maps and stuff like that, softwares and drones, and some machine learning that we're gonna talk afterwards. Okay, so there are two types of remote sensing. There is active remote sensing and passive remote sensing. So the active remote sensing, so for example, here we have a satellite, and the satellite is going to send some signal to Earth. And of course, for example, is going to conduct some research about the atmosphere of Earth. So the signal that he sent, the wave that he sent, is going to be altered in the atmosphere, the atmosphere layer of Earth, and is going to be sent back to the satellite. So if the source is the satellite, it's active remote sensing. But if the source is not the satellite, it comes from any source. For example, here we have the sun. It's called the passive remote sensing. So if the sun sends its radiation towards Earth, and it gets reflected to the satellite after getting the information, after altering the radiation in the atmosphere or in the land or whatever you're conducting research on, the satellite gonna capture that radiation and it's gonna analyze it. So this is the difference between active remote sensing and passive remote sensing. Basically, the sources, if it's natural, it's passive. If it's artificial, it comes from the detector itself. For example, the satellite, it's active remote sensing. So we have some different satellites that actually doing amazing jobs in remote sensing and capturing really amazing details of Earth, like Aura, Parasol, Oko, Aka. So there are CloudSat, Calypso. So there are many others. So to talk about remote sensing and stuff like that, let's talk about the height, or let's say the orbits in which we can put the satellites. So there are 3 orbits. There is base orbits, there are medium orbits, and there are very high orbits. But in this particular geostationary orbit, in the 35,786 kilometers away from from Earth, of course, away from the sea. Let's say if you count a sea as 0 kilometers here, if you put any satellites here, it's gonna stay at its place and it's gonna rotate the Earth directed at a singular point. For example, if I'm currently in Hungary, for example, so if I'm gonna put the satellite, I'm gonna send the satellite and put it here. is going to be directed towards Hungary, and even if the Earth is rotating around itself in 24 hours, 23 hours, and so the satellite is gonna never change, and it's gonna be always on top of Hungary. So the Hubble Space Telescope, for example, is placed here, around from 0 to 1,000 kilometers, precisely 595 kilometers, and our detection, our satellite detection, our remote sensing the satellites, we can actually put it in the medium orbit or in the high orbit. We can sometimes put it in the bass orbits, in polar, for example, in polar orbits. Let's say for instance, these orbits, for example, we have too many satellites like GPS, Galileo, Hubble, like I said, and many others. So basically, the satellites that we can put in lower orbit is satellites that goes from pole to pole. So these satellites tend to have, let's say, capture the land and, for example, the sea, or it has to capture an image to for example, to then analyze it and find the results. But there are many orbits that we can talk about, but obviously we don't have the time to discuss all the orbits. So these are some types of satellites and the instruments of satellites. They are really complex. Like we can see the solar panels, because the satellites are eventually powered by solar energy, and some captures for example, this is solar orbital instruments, so it detects anything related to the sun. So the idea behind it is, let's take the active remote sensing. So the satellite is going to send some signal, and we're going to receive it back after it being altered in the atmosphere or in land or in any other any object where we want to research, and we want to have information about. So we have here the whole spectrum, not altered. So we send the spectrum. We send this spectrum, and you can see that the spectrum get absorbed by the object, or absorbed by the land, or absorbed by the sea, or absorbed by any object that we're gonna study. Some spectrum is gonna be absorbed by the object, and is gonna be returned back to the satellite. So if we have a missing, for example, if we have missing layers here, like we see here, we have a precise, let's say, a precise idea about the elements composing that object. For example, each element has its, let's say, fingerprint. So, for example, an element has the green in the green spectrum. If we notice that the spectrum that we send, the object observed the green spectrum, then we can conclude that the element that has the green spectrum is inside that object. So basically, the spectrum idea and stuff like that, this is basically what we do to know the composition of some elements, and to have mapping of Earth, and we can do it as well to stars and stuff like that. So the satellite that we have here is a polar satellite, so it goes from a pole to pole, and like we can see here, it has it maps the surface of Earth and is conducting some images about the surface of Earth. But because the satellite is moving, it's conducting it square by square. So like you can see here, and then we can put the squares besides each other, and we have the full picture. So The problem is our instruments are not very advanced to capture for example, to capture this colorful image. So what we do is we have instruments that captures, for example, the red spectrum, and the green spectrum, and the blue spectrum. And then what we need to do is superpose the images on top of each other to have the colorful image that we have here. And for example, to look for crops or stuff like that, we need infrared, the infrared part of the spectrum, because of course it's necessary to have the infrared spectrum to know where we can plant our plants or crops or whatever. So if we mix the infrared spectrum and the red and green, for example, we have this colorful image that states, as you can see, the parts, the red parts, that states where exactly we can grow crops. So this image, for example, it has a different approach, let's say, and it's done by the same way. The satellite is mapping the Earth and stuff like that, but the difference is it is mapping according to some variables, and as you can see, it's different. For example, we have the blue one, we have the green one, and we have the red one. And this meters here, we can choose any variable because we have many instruments in the satellite that can conduct such a mapping. So for example, if you're gonna take the height of a surface, let's say that the red parts are the most high, the highest parts in the surface, and the blue parts are basically a plain, or it's not a mountain or stuff like that. So this kind of measurements we can do as well, doing the remote sensing using satellites. And this is a picture taken from Brazil. In some places we can actually detect where we can, like you can see here, there are many colors, and like you can see here, for example, the blue color here states the abandoned single cropping. And of course, we can't detect using the remote sensing, using the satellites that we have directly like that, we're gonna have all the results. That's why we need machine learning, because, for example, we can have a mapping. We can have the surface of this area of Brazil, but we can't directly have the results. We can't directly have these results. That's why we use machine learning. Machine learning is when you put some commands or put some inputs, let's say, in a machine, in a computer, let's say, and that machine is gonna have the output of that command, and is gonna alter each time the output depends on dependent on the input that we have. So there are many types of machine learning, like supervised learning, unsupervised, and sub types like classification, regression, and clustering and association. Classification, when you classify some parts of the map that we have, for example, like this one. And regression is basically the linear line that we have, linear equation that we have between two variables or more. So the clustering, when you put it in some bubbles and you see that this is the type A and this is the type B, for example, and also an association, when you associate pictures with different different properties and different variables. So this is the basic supervised and unsupervised and reinforcement learning procedure. So the input is given in, and the output is out of the computer, and there is a critic happening, and there is an error to modify the input, to modify the output of each time. So they have the mapping and classes and stuff like that. So these are an image of a regression. So we have two variables here, one variable here and one variable here, and we conducted many images. Let's say, well, many. I mean, the variable are not related to the topic of today, but bear with me. So we have many essays, we have many images, and we found that there is a linear relation between the two variables. So after tracing a line, we can, why we're doing this? If we have one variable, for example, if we have, for instance, we have the expansion of double cropping, we can, if we have the linear relation between, for example, the expansion of double cropping and the abundant double cropping, we can, with only the results of the expansion of double cropping, we can have the results of abandoned double cropping, because there is a linear relation between the two. So this is an image of the classification problem, or clustering. Let's say clustering, because classification is another thing. So we conducted many images as well. The variables are not in the topic of this conference, but we conducted many images, and we can see that we can circle this cluster, and we can circle this cluster, and we can circle this cluster. And this is basically called classification or clustering. Those who have basically the same, let's say they're related learning methods. And the most famous application of remote sensing is, for me, is the Copernicus Mission, which is funded by made by the ESA, so the European Space Agency. Is the Europe's eyes on Earth. So basically, the Copernicus mission is to send many satellites in Earth, around Earth. Sorry. So to conduct some research in climate change, marine monitoring, land monitoring, security, and many more. And we have many satellites that can detect some properties of Earth. And for example, emergency management, if you have an earthquake coming or anything, you can detect it through satellites, and we can prevent a catastrophe. So we have all the satellites. Each satellite is called Sentinel. So Sentinel-1, Sentinel-2, 3, 4, and there are many Sentinels. And from Sentinel-1 to Sentinel-6, for example, as we can see, each Sentinel, each satellite is for a specific job or specific mission. So, for example, let's say Sentinel 5 and 6 is for example, to climate change or atmosphere monitoring or stuff like that. So each Sentinel is for specific mission to have. And this is the Copernicus.eu. You can check it out, and it's a free source. You can download any image, any mapping whatsoever about Earth done by practically remote sensing, and it's a free database. You can check all the climate change, marine monitoring, atmosphere monitoring, and many others. Anyone can log in, just make an account, and you can have all the database, or practically a major part of the database of the Copernicus. So it was a short Astrotalk. So it's an initiation for the curiosity of people that are.
Thank you, Amin, so much. It was a very nice presentation. You just talked about
the other information that I didn't talk about. So thank you for your attention, and thank you.
Thank you, Amin, so much. It was a very interesting and amazing presentation. You already covered a lot of points about spatial data and space mission also, and the data that we can use, in fact, in space activities and also imaging, in fact, because we cannot also forget that some of the image, even the one that we use for mapping or for planetary surfaces, are coming from space mission, and also some also for the Earth mapping. In fact, we are using orbit data from mission around the Earth. So I will leave the question for the participant here before going to collect the question on the social media. And I will just open parentheses, and I would like to welcome Professor Ahmed Shalan. He is from Lebanon, and he is joining us today in this amazing talk. Hello, Dr. Ahmed Shalan.
Hello, how are you? Good morning, everybody.
Good morning, good afternoon, good night.
Good night, okay.
From which time zone we are all different. So I would like to welcome any question in case you have here before moving to the social media comments and question. I don't know if someone have a question. So I will collect some questions that we got from Facebook and for Twitter. So what kind of data can we get? This question is for you, Amin. So they said, what kind of data can we get from orbiter? Is there only image data or radar data or another kind of data, in fact?
Can you repeat the question, please?
What kind of data we can have from a space orbiter? Like, do we have only image or radar data, or there are other kind of data that we can collect?
If we're talking about remote sensing, we can have everything. That's why I showed the Copernicus mission, because in the Copernicus mission, we have the land monitoring, the sea monitoring, and many other properties that we can, information that we can conduct in remote sensing. So basically, everything that we can detect by the instruments that we have in our satellites, we can have results from, and yeah, basically that's it. But to reassure that there are basically hundreds and hundreds of data that we can check, free data that we can, open source data that we can check, and yeah, basically it's much it.
Thank you, Amin. The next question is, how is remote sensing used in space?
Remote sensing, to have the definition of remote sensing basically is to any information that you have from an object that you can touch, see, taste, or feel, or whatever. So if the five senses of the five human senses is not altered in the in this detection, then it's a remote sensing. So basically, in deep space, I'm not gonna call it remote sensing, because it's basically we capture light. So well, you can name it remote sensing if you suppose that the source, it's a passive remote sensing when the source of the remote sensing is, for example, a star or a galaxy or whatever. But remote sensing is linguistically related to a small region, like not for deep space. I mean, you can name it remote sensing, but we don't usually say that it is remote sensing when we're talking about space, deep space imagery.
The next question is from Iman Hajri. Ma'am, Iman Hajri, she said, how to extract building by satellite image?
I'm not quite sure how to extract
buildings.
myself.
Yeah,
So if you're talking about the imagery, for example, like the famous Google Maps, so how to do that? Basically, they have satellites that, like I showed in the slides, there are many types of satellites. There are a polar satellite that goes from pole to pole, and there are satellites that are in the medium range of orbital Earth orbits. So there are many types of satellites, but they detect the Earth by just pixel by pixel, let's say. So, and of course, to have a good resolution of that picture, we use very high cameras. Let's say it's not a camera, of course, but let's name it a camera. We use very high resolution cameras to detect exactly the buildings. And yeah, basically the satellites that with Google Maps, I mean, they have good resolution, but basically the first and the only purpose of them is to detect the surface, the clear surface of Earth.
Thank you, Amin. The next question is about what type of data is remote sensing?
What type of data is remote sensing?
It is orbit data, it is image data, it is radar data.
Anything, actually, anything that you can, any information that you can have from any object not using the 5 senses is called remote sensing. So it could be an image, it could be numbers, it could be binary numbers, it could be anything. So if it's an information that is not gained by the 5 senses, it's called the remote sensing.
The next one is why are satellites important for remote sensing?
Well, satellites, basically, without satellites, we don't have phones, we have internet and stuff like that. For remote sensing, without satellites, the remote sensing is only conducted in Earth. So in small regions, in meters and hundreds of meters in Earth. But if we're talking about satellites, we're talking about we're talking about a vision, or let's say the vision of the satellite is different than the vision of our human vision. So there are some information that we cannot gain by our instrument in Earth, basically not because they are not efficient, but because the only reason, because if you are thousands of kilometers away from Earth, you can see the whole picture. For example, in let's say in clouds, to detect if there is a tornado in anywhere on Earth. So to detect if there is a tornado, we need to go far away from Earth, thousands of kilometers away from Earth, to have the full picture of Earth, and to have the other analysis to basically detect the weather and stuff like that, to have the result if there is a tornado or not. So yeah, basically it's a wide vision of things rather than to do it on Earth with our instruments that only have the range of meters and hundreds of meters.
Thank you, Amin. The next question is from Suha. She said, what are the benefits of remote sensing? What we can do with that?
The benefits of remote sensing, like I talked, that's why I showed the Copernicus mission. Basically, the Copernicus mission like summarized everything that we need in the that basically the remote sensing help us in daily stuff. So in climate change, in marine monitoring and atmosphere monitoring, let's say for example atmosphere monitoring, we will not know the next day, if the next day is gonna to rain, or if there is snow or whatever, without using of satellites. And land monitoring, because agriculture with satellites evolved exponentially with satellites. So with the mapping of the surface of some surface of Earth, we can detect if that a certain plant can be grown in that surface without analyzing small portions of the land and stuff like that, that will not eventually have efficient results. In the most cases, emergency management is part of the Copernicus mission as well. So in emergency management, we can detect any catastrophe like earthquakes, volcanoes, even before they volcanoes before they erupt, or earthquakes before they happen. So yeah, we can actually save lives and make human life easier.
Thank you, Amin. The next question is from Ibrahim Abdul Karim. He said, how is the satellite can take close-up pictures in cities by a wide field camera?
Actually, that's a very good question. So the satellites have, of course, they have the wide field camera. We call it a camera, but basically it's not the same camera as, for example, our phones or the camera that we have in our PCs. So the wide field camera, like Ibrahim said, can have a very, very high image in dimensions, but to detect the full clear pictures of the cities and buildings, like I believe Eamon said, to detect the full picture or clear picture, we have to go, like I said, pixel by pixel. So if the resolution of the camera is very high, very, very high, and I don't have the exact number in my mind, but if the resolution of the camera is very high, no matter what, if it's a wide field camera or a short field camera, no matter what, we can detect clear pictures of Earth. And like you see in Google Maps, you can see cars and buildings and even small even persons. So yeah, that's about it.
And then the last question here is, what are the advantages and disadvantages of remote sensing?
Well, I think I talked enough about the advantage of remote sensing. Like I said, the Copernicus mission, which had the land monitoring, marine monitoring, atmosphere monitoring, and many others. But the disadvantages of remote sensing, actually, if we're talking about satellites, if we talk about remote sensing from only a satellite, maybe the debris or maybe the leftovers of the satellite that we're gonna have from tens of years, from years and years of sending satellites. Right now, we don't know how to deal with those satellites that we send. Some satellites crash, and some satellites go to, in orbit until they malfunction and they're wasted. They stay in orbit. So basically, let's say the most disadvantage about remote sensing using satellites are the leftovers of the satellites around the Earth. So it will have a cloud around the Earth that will somehow in hundreds of years will cover maybe a big portion of the atmosphere, and we'll have many problems in sending other satellites, and we have many problems in sending, for example, habitable missions in, let's say, in the near future in Mars and stuff like that. We're gonna have many problems. The debris of the satellite gonna cover the Earth, but this is a long-term disadvantage. So it will happen not in a few years, but in hundreds of years.
Thank you so much, Amin. I don't know if I have just small, very tiny question about could we use like remote sensing data, for example, to as I say, it's the same question of, I think, of another colleague here, like for building collapse or to for building construction, let's say, is that something can help for building collapse or to avoid a human catastrophe, in fact?
Yes, actually, if we gonna have the image, or not the image, but if we're gonna concentrate our satellite with the exact instruments, we're gonna have the whole map of the tectonic plates, let's say, and we're gonna have the results of those movements of the tectonic plates, and maybe have earlier notice of the earthquakes and many other security risks that we're gonna basically we're gonna face during living in Earth. So yeah, it helps us. It really helps us, and the security management grown exponentially using satellites, because the instruments that we use on Earth are efficient, but they don't take the full picture of that, and we cannot prevent those from happening with the instrument only on Earth, because we only detect, but we can't see the full picture, so we cannot prevent that from happening.
So I don't know if someone here have something to add or comment or a question before we close out the session of tonight. Okay, I think no more comment or question, and also we collected all question and feedback from social media. So it was very interesting lectures. I'd like to thank you, Amin, for your amazing presentation. It was really very interesting. And I would also to thanks our participant here from Lebanon, from Egypt, from Mauritania as well. Thank you everyone for being part of our meeting today. And I will also, in fact, take the opportunity to invite you for tomorrow's lectures, in which it will be held at the same time, in fact, at 17 GMT, which is equivalent to 8 p.m. Central European Time. And our speaker tomorrow, it will be from the USA, who is Dr. or in fact, he is amateur astronomer Mike Simmons, and he will talk about how astronomy could be a peaceful link between the whole planet. So Mike Simmons, we will give tomorrow his lecture at 8 Tunisian time, 7 p.m. Central Europe GMT, Greenwich time, and 8 p.m. Central European time. So I would be glad to see you tomorrow at Mike Simmons' talk. It will be also held in English, but we will provide translation in case it's needed. So thank you everyone to be here today and to be part of our meeting. I hope to see you tomorrow with Mike Simmons, and thank you again, and see you the next time. Bye-bye.
Thank you. Goodbye.